Good evening, everyone. Welcome. My name is Jean-Luc Margot. I'm the current chair of the Department of Earth, Planetary, and Space Sciences, and our mission is to understand and protect our home in the universe. I'm thrilled that so many of you are here today to celebrate our alum and to hear about the amazing story of Plate Tectonics. We're very excited about this evening's event because it celebrates the accomplishments of one of our alumni. And our alumni expand the boundaries of human knowledge. One of our greatest satisfactions as professors here at UCLA is to see our students go into the world and change the world. Today's students are tomorrow's leaders and innovators, so this event is very exciting for us. If you go to our website and go on the alumni section of our website, you will see an impressive list of professional outcomes of our students, whether it is in academia, public service, or industry. We're also excited about tonight's event because it is well aligned with our outreach mission. In the past year, our department has probably touched about 20,000 curious minds. And if you go to the outreach section of our website, you can learn all about our events. And you can also find a form to request an outreach visit for your school, for instance. Our next outreach event is the annual Exploring Your Universe Science Festival. This is a wonderful, fun event. It's free and open to the public. We expect between 5,000 and 10,000 people on campus on Sunday, and this event has been organized by UCLA graduate students, and we've been a part of it since its inception, and we're very excited about it. As I said, it's organized by our graduate students, and the 70 or so graduate students of our program play a key role in fulfilling our mission. They provide the bulk of the research results during their training here at UCLA, and we are very eager to improve the support for these students. It comes from a combination of things, teaching assistantships, grants, and philanthropy. The teaching assistantships support about a quarter of our students. Grant support is what covers most of our graduate students, and that presents some difficulties because federal funding is competitive and it fluctuates. So one of our top priorities as a department is to secure additional fellowships for our graduate students that can provide a stable source of funding that come out of an endowment. So we're raising funds, for instance, to name a graduate fellowship to honor Professor Margaret Kivelson, who gave a lecture here a few months ago. Some of you were here. And she has since received yet another prestigious award, and she was profiled in the New York Times on October 8th of this year. So there's currently an extraordinary opportunity at UCLA that qualifying gifts towards endowments receive a dollar-for-dollar match with funds available to the Dean of Physical Sciences. So if you believe in our mission of education, research, and outreach, but you can't contribute at the endowment level, you can partner with us at other levels, and some of the examples are listed here, and you can make a real impact in the student experience and the programs we can offer. One of the initiatives I'd like to highlight is the first ever crowdfunding campaign that is going to launch on November 8th, and that will support student field trips. So over the last decade or so, we've been privileged to offer many field trips at minimal or no cost to our undergraduate students, thanks to the support of our donors. These trips offer the next generation of students and UCLA alumni an opportunity to blend the knowledge they learn in the classroom with the kinds of eyes-on and hands-on experience that only time in the field can provide. So for instance, last spring, 11 students visited Kilauea volcano and witnessed high activity levels just 2 months prior to the eruption that destroyed about 700 structures and caused the evacuation of 2,000 people. This was a tremendously invaluable experience for these students, and we want to continue sending students in the field. So I wanted all of you to be the first to know about this crowdfunding campaign and ask for your support. Donations of any size, even a few dollars, make these field trips possible. So you can learn more about our field trips and this campaign on our website at epss.ucla.edu. We also have donation forms in the back if you prefer not to donate online. Today's speaker is Dr. Dave Bercovici, who is the Frederick William Beinecke Professor of Geophysics at Yale University. Dave got a BS degree in physics from Harvey Mudd College and a PhD degree in geophysics and space physics right here at UCLA. He spent about 10 years as professor and then chair of the Department of Geology and Geophysics at the University of Hawaii, prior to moving to Yale University in 2001, where he has also served as department chair on 2 separate occasions. He is the author of 3 books and the recipient of numerous awards, including election as a fellow of the American Geophysical Union and election to the US National Academy of Sciences. We will have a question and answer period after the talk. If you have questions for our speaker, please write them down on an index card that we're passing around, and our student volunteers will collect them at the start of the Q&A period. So now please join me in welcoming Dr. Dave Bercovici.
All right, thank you. Let me switch to my actual talk. I could use Jean-Luc's slides, but can only go so far. Okay. Let me see. Here. Okay. So I have about 2 hours to talk to. All right, so I'm going to talk quite a bit about, well, this talk, as you can see, is about plate tectonics, and try to put this in the context of trying to use, plate tectonics as sort of the grand theory of the Earth, which we have been taught, when I was a student and even when I was an undergraduate, we were being taught about plate tectonics as the grand theory of the Earth. But I want to sort of explain to you why it's important for societal reasons, and why it is also sort of the grand theory of understanding the evolution of the planet. Hopefully I will have time to get all of that done. So this, of course, is one of the events that we saw in 2010 at the Eyjafjallajökull eruption, and I'll get to those a little bit later, but I want to jump right in and talk about one of the major events. It's probably the biggest earthquake that has occurred recently, amongst those earthquakes that are sometimes called Megathrust earthquakes, earthquakes of magnitude 9. Okay? In California, you may be used to ones that are magnitude 7 or so. These are about 100 times larger in magnitude, maybe 300 times larger in energy. This was thought to be about a 9.0 earthquake that struck off the coast of Japan. And those of you who remember the news from 2011, seeing these images of tsunami run-up causing a lot of damage in these prefectures of Miyako and Sendai especially, that then wind up causing flooding that rushed in many tens and even 100 kilometers inland, inundating farmland. You can see even the waves cresting over the tops of these trees and causing billions of dollars of damage. And of course, the big event was that it wound up flooding the Fukushima power plant, because in essence there was, it's maybe arguable, but there was a miscommunication between the engineers who built the plant and the seismologists who were there. And of course, the Earthquake Research Institute at the University of Tokyo was one of the preeminent earthquake or geophysical institutes, but they wound up building their seawalls around that power plant too low for what is known to occur for tsunamis. They flooded the core, caused a rupture of the core and spewing of radioactive gas that they're still recovering from. So this is one of the bigger events, and of course I'll show you plenty others as we go along. And sometimes you see these events, and we've seen a series of these megathrust events and other volcanic events, and everybody always thinks, well, this is unusual, it's end of days, it's caused by climate change, who knows what, okay? This is probably all, nonsense, but the real question is, how unusual is this? Okay, and of course, one of the lucky things, the great things about being a geophysicist and geologist on this planet is probably the most active and one of the more interesting planets in our solar system, because we can look at just one day's worth of earthquake, and I did this morning at about 8 a.m., okay? Just anybody can do this. You can go to the USGS website and you can plot out what are the number of earthquakes that occurred just within the last 24 hours. And this is just 24 hours worth of earthquakes. And in fact, at the time I plotted it, there was a red one down here earlier that showed it happened in an hour, but then I diddled too much, and then I guess it was more than an hour by the time I finally captured this image. But this is about a week, okay? And this is about a month, okay? So just within 1 month, you can see a lot of activity occurring, and the size of the circles, the color of the circles represents when they occurred. White is about a month, but the size of them also indicates the magnitude. So 1 month ago, there was the earthquake in Sulawesi in Indonesia. Okay, it was about a 7.5 that I'll talk a little bit about later. That caused a tsunami and about 2,000, a loss of life, about 2,000 people. Okay. So what causes this? What causes all this activity? We'll see. I'll talk a bit about earthquakes. I'll talk a bit about volcanoes. I'll try to give you a flavor for it. But that is, in the end, most of it is fundamentally caused by the movement of tectonic plates on the surface of the planet. Again, we probably have the most active terrestrial planet in the solar system, perhaps one that we know anywhere yet. And so in a way, we can think that it explains almost everything. And a lot of this is what we would be typically taught. I'm going to give it to you in 30 minutes, okay, what you're going to get, you might get as an undergraduate in geology, but it explains almost everything. So we'll talk a bit about earthquakes, volcanoes, at least to give you some sense of the rules of thumb. It isn't just that these events occur at what we call plate boundaries, but the flavor, the direction, or the way the plate boundaries act also tells you how big the events are, which is quite important. I'll try to touch a little bit on how important it is to understand the history of climate on our planet, okay, why it is we're here, okay, as animal life forms, is probably owe that to plate tectonics as well. Again, these are theories that go around that people have tested, and it's still a matter of debate and development. And also, it's thought that the origin, or one of perhaps the sites of origin of life, when the surface of the planet was hostile, was probably also due to plate tectonics. If I have time, I will touch a little bit on what I do, which is try to understand why we have plate tectonics from a physical theory of understanding why our planet has it, whether we expect to have it on other planets that we might be able to predict from basic physics. Chances are I won't get there, okay? But at least you get something out of this, okay? So in the beginning, I always say the real beginning is 13 billion years ago, but in the interest of time, we'll skip 9 billion years, okay? And we'll just go to about 4.6 billion years ago when the solar system was created and the Earth accreted very rapidly with respect to geological time frames. Usually that you have to form the solar system within a few tens of less than 100 million years before the sun lights up and blows everything out. So about 4.6 billion years ago, the solar system of the planets formed pretty rapidly. And much of the energy of collisions, even you think of collisions caused by asteroid impacts, depositing energy and causing damage, and that's just sort of the late stage of the Earth sweeping up stuff that hasn't been used to make planets. Deposit of this as energy is heat, okay? And a lot of that heat is still left over inside the planet as primordial heat, the heat that is just deposited from the formation of the planet, and it is still leaking out to this day, almost 5 billion years later. Okay, so if we ask how much heat is coming out of the planet now, it's about 50 terawatts or 50 trillion watts, okay, that is coming to the surface. Probably more than half of that is from the heat left over from the formation of the planet, and probably less than half of that from the decay of radioactive elements like uranium and thorium that put out a significant amount of heat as they wind up ejecting sort of heavy particles like alpha particles, which are helium nuclei. So this is the fuel. That is the energy source for geological activity. And it looks like it's a big number. 50 trillion watts sounds huge, but it's a big planet. When you spread it out over the whole surface of the planet, it's actually kind of a tiny number. When you compare it to what is coming in from the sun, it's about 4,000 times smaller than what we're getting from just regular solar heating that keeps us warm and happy and alive now. Okay. So why is it that we even have sort of geological activity, given that it's not a giant source of energy? I guess one other example I could put out there is that if we were to take this amount of energy, spread it over the surface of the planet, it would be about the equivalent of one light bulb in a football field. I mean, you wouldn't even be able to read by it. Okay? So, of course, what focuses this energy is the action of mantle convection, which I started studying here with Jerry Schubert, who's sitting over there, okay, looking at me, wondering if I'm going to tell some lies or not, but give me time, I'll get there. Okay. The Earth's mantle convects. It's solid. It is not liquid. We always try to drill this into our students' head that it's not convecting because it's liquid or molten. It's a solid crystalline matter that flows very, very slowly. It's about 3,000 kilometers of solid rock between the crust, which is a little sludge on the surface. Sorry to those crustal geologists, but that's the way it goes. Okay. to the core, which is about 1,800 miles. And the rock near the surface cools, is heavy, and eventually wants to sink. The rock near the bottom, near the hot iron molten core, the core is, at least the outer core is molten and moving around. It's a whole other subject unto itself, is heating it up and causing the hot stuff to rise. So convection is cold stuff sinks, hot stuff rises. That's basically what you need to know. Right? So this is sort of a computer simulation from a colleague, Shiji Zhang, who's in Colorado, showing cold stuff falling from the surface and sinking and spilling over the surface of the core. Hot yellow stuff rising off the core, these blobs or plumes, okay? And this is thought to be what convection might look like. Okay? And it's very slow, and when we say things like it's 1 to 10 centimeters a year, you don't have a good feeling for that. Okay? Nobody really can sit around and watch 10 centimeters occurring, spreading out in a year, but in a way you have regular experience from it because it's as fast as your fingernails grow, or your hair, if you have hair. Okay? But it's at least fingernails. Okay? You don't just shave it off all the time. Okay? So the manifestation of this convective motion, hot stuff rising, cold stuff falling, is plate tectonics. And that's the first thing we always try to say, those of us who study mantle convection, say that plate tectonics is convection. Okay? It used to be thought that convection was driving these plates around like they were rafts, but we would argue that's not really the case. Plate tectonics is where the surface, coldest rock is heavy and sinks along these regions called subduction zones, where these big slabs of cold rock move to the side and they sink down into the mantle, and they are going to cause, as you're going to see later on, a lot of the geological activity that I'll refer to soon. Okay, it causes melting and things like that. So we'll get to all the details in a bit. It also causes the plates to rip apart, okay, and the mantle fills up, rises up to fill the gap, and it causes some melting. And again, we'll get to all of that a little bit. But the basic point is that plate tectonics, as we think of it, is really mantle convection. Cold stuff sinks, and especially cold stuff sinks along what's called subducting plates or subducting slabs, big slabs of rock sinking into the mantle. Okay, you're going to hear a lot about slabs. Okay, the surface expression of plate tectonics is that the idea is that the surface is broken up down to about 100 kilometers of cold, strong rock, varying in thickness, okay, into about 12 major plates and a bunch of little small plates. And they fit together like puzzle pieces. And all of these pieces move with respect to each other, okay, and how they rub against each other, how they spread away from each other, how they collide with each other, it determines the nature of the plate boundary. So the Pacific plate is the easiest one to look at, and it's where we are right here, okay, that as it moves off basically towards Japan, it is colliding or diving down under this plate here, which is basically Eurasia. Okay? It dives down in what's called a subduction zone or convergence zone where things come together. It spreads apart away from South America against this other plate called the Nazca plate, called a divergence zone or a spreading center. And it's moving sideways right here where we are along the San Andreas Fault, but along other areas too that we'll see, like Queen Charlotte Fault and down here next to New Zealand and whatnot. Okay? But our favorite one here is San Andreas. So that gives you an example of what we say with plate tectonics. If any questions or interruptions, please feel free. Okay. What else do I want to say about that? That's pretty good. Okay. The types of plate boundaries in this cartoonish version, again, is where the plates dive underneath. You know, sort of an overriding continent. They're heavy. They sink. Is again a subduction zone. Where they slide by each other is sometimes called a transform fault. Where they spread apart from each other is a spreading center. Okay. Again, another image of this, even more simplified, divergent, pulling apart, converging where they're subducting, sliding by each other. I'm just drilling this into your head so that you will hopefully remember it in a few more slides. Well, I like history. I mean, it was always one of my favorite topics, and the history of this problem is actually pretty fascinating. The idea that things were moving around is not something that recent. I think I even mentioned in an abstract that it's almost 400 years of accumulated knowledge, especially when coastlines started to be mapped out, and even Francis Bacon noted the parallelism of the coastlines between Africa and South America. You can continue to go down to these various ideas. Edward Seuss suggested the Gondwana land, and of course most people were being taught that Alfred Wegener proposed this idea of continental drift in the early 20th century, where he said that he had these various lines of evidence that continents were drifting around and moving apart and had formed supercontinents, and his version was Pangea, which is still a term we use today. And people tried to propose, how could this be driven? He thought it was driven by centrifugal force. Continents were being swept to the equator. Other people, various other people proposed, like Arthur Holmes and others, proposed that it was being driven by convection. Arthur Holmes was one of the first people to raise the idea that convection was driving plate tectonics. Although the idea of convection actually existed even in the 19th century, when the great debate about the age of the Earth was raging on. But that's a whole other story we don't have time to go into. One of my heroes of, well, here I should comment this, okay, that the theory of continental drift was basically rejected in about the 1920s, 1930s, probably thanks to a lot of American geologists, okay, and especially to the British physicist Harold Jeffreys, who argued correctly that it would be impossible for these continents to move because Wegener proposed that they were just plowing through like icebreakers through the oceanic crust. Okay, they're just blasting through the crust and moving around that way, which Jeffreys proved would be really impossible. So it went by the wayside, and people who wanted to study continental drift were advised not to because it would be a career record. So there are various great papers from the 30s where people wrote about it, and then they never saw them ever again because they were warned not to work on this crazy idea, or else that would be the end of their career. So later on, about in the late 50s and the 60s, there started to be the accumulation of even more evidence, okay, that led to plate tectonics. And one of my heroes is Harry Hess, not just because he was a Yale graduate. I just worked there, okay? But he was, after going to Yale and becoming a Princeton PhD and a professor there in the 1930s, he joined the Navy, largely to try to get access to naval ships, not only to contribute to the war effort, but also to use the ships to basically try to map out more information about the seafloor. And he was involved with various famous landings in the Marianas, in the Philippines, and Iwo Jima. And while he was going through the various landings, he was basically illegally running the sonars off the back of the ships, okay, to map out the seafloor. I mean, he wasn't supposed to be doing that because they would basically tell the submarines where they were. But he did it, and he basically wound up figuring out a lot of the topography and the shape of the seafloor from doing that. And he was the one in about 1959 wrote a technical paper that proposed the idea of seafloor spreading. And then he published it again in 1962 in Nature, okay, proposing this idea that the seafloor was actually spreading apart at ridges. And this was verified later by the work of Vine and Matthews and an unpublished paper by the Canadian Lawrence Morley, okay, that proposed that, well, don't wish I had time to go into this, but they basically, by observing what's called magnetic lineations back around the time of the Cold War, we wanted to figure out where submarines were hiding. So they basically had very highly sensitive magnetic measurements to go back and forth and figure out where if you saw any sort of magnetic type object like a submarine. And they wind up finding that going back and forth over these big undersea mountain ranges, which they didn't know were spreading centers, they saw these symmetric patterns of magnetic lineations that basically told you whether the rocks were magnetized up or down. And again, I wish I had time to go into that, but I don't. But that was the major discovery that said that there was seafloor spreading. Then around 1968 was really the theory of plate tectonics. Not the discovery of seafloor spreading, or it was the mathematical theory that explained big plates as big puzzle pieces moving with respect to each other, done somewhat independently by Jason Morgan, or independently by Jason Morgan and Dan McKenzie, and Xavier Lapichon also contributed, some of these fundamental papers to this. And it's a big deal now because it's 50 years. It's a 50-year anniversary, and I was just at a meeting in the Collège de France a few months ago where these folks were speaking, talking about, and us young Turks were speaking too, in the 50th anniversary of plate tectonics. So, big deal. Happy birthday, plate tectonics, okay? So let me get to why we care, okay? So one thing we could say is we know that earthquakes and volcanoes mostly occur, not all of them, okay? And the ones that do not occur on plate boundaries are fascinating unto themselves, but probably the majority of them occur on these plate boundaries because these big rigid plates are moving by one another, either colliding or sliding by each other, okay, that wind up causing friction and leading to earthquakes, or they wind up causing melting for different reasons, which I'll get into, that wind up leading to volcanism. So why it's important is not only does it tell you where not to live, like Southern California. No, okay. I mean, there are worse places, like Florida, but that's a different reason. Okay. But it tells you where most earthquakes occur, but it also tells you the kind of earthquake. Okay, the way that the plates move with respect to each other will tell you how big the earthquake is. Okay, and so it doesn't predict when the earthquake's going to occur, but it tells you where they're likely to occur and how big they're likely to be. Okay, so that's a very important part of the plate tectonic theory. It's not just cool that it looks like a bunch of puzzle pieces and that it tells you where the action is, but it also tells you how big that action is going to be. So what is an earthquake really? So an earthquake is when you have two crustal rocks, basically you have two tectonic plates way off on either side of where this line is, and they're moving inexorably forward very, very slowly, as fast as your fingernails grow. Okay, and the rock between them is slowly, slowly bending, and eventually the stress on the rock builds up enough that it breaks and snaps, as if you were trying to bend a pencil and it eventually breaks. There is a misconception that when this break occurs and the rocks basically lurch away from each other after the break, that the whole plate is moving. Okay, that the whole Pacific plate is moving forward and the other side is moving, which is not true. Okay, it's just this rock in the vicinity that's moving. The two plates on either side are just slowly, slowly grinding forward. Okay, and these plates, these earthquakes are just breaking and chattering and catching up with the plate, and that's all that earthquakes are doing, this little chattering motion catching up with the plates as they move forward. And this rebound after this lurching basically sends these seismic waves out, which wind up causing what you think of as earthquakes. Okay, so the types of earthquakes we see on plate boundaries, just as a rule of thumb, okay, is that at spreading centers, the plates are very thin. Basically, they have zero thickness. They're very thin, they're hot, they're weak, they're under tension. Okay, so under tension, there's less friction, so they have small earthquakes. So we don't really care about the earthquakes at these mid-ocean ridges. They tend to be about magnitude 2 or less. They occur all the time, but they're just not, societally significant. Transform fault earthquakes, where you have plates sliding by each other. Okay, this is where the plate is sort of intermediate strength, and it's not under compression, except in California, where they're under a slight compression, where your biggest earthquakes occur. Okay, but they're generally under shear, and the earthquakes are moderate. I know people living in California think a 7.0 is big. It's not, sorry, okay? Not compared to what we see elsewhere in the world. Subduction zone earthquakes, okay, this is where the plates are thick, they're cold, when they bend, they store a lot of energy, and this also, the system is under compression, so it builds up even more friction where the plate slides underneath sort of this, in this example, the continental plate underneath it. So in those cases, you get these enormous earthquakes. Once in a while, there's anomalies, okay? But usually in these subduction zone environments are where these giant earthquakes occur. So quickly, when it comes to transform fault earthquakes, we're all used to the San Andreas Fault, where there's two plates are sliding by each other on either side, but where there are bends in the fault are really where the bigger earthquakes occur, because they wind up, the plates catch on each other. Okay, especially if there's a little bit of collision, basically one plate trying to grind into the other plate, that's where you typically get the larger 8.0s or so, but they tend not to get much bigger than that. Of course, the year I graduated from here, 1989, was the Loma Prieta, the World Series earthquake, which occurred on the bend in the San Andreas near the Santa Cruz Mountains, and those of you who will remember it, you remember the collapse of the 880 overpass and a lot of destruction in the Marina District, and a lot of that is also just due to crappy construction, sorry to say, but they're basically building it on sediments and old rubble left over from the 1906 earthquake, which I wish I had time to talk about, but I don't. But even in that regard, there was some loss of life, and we compare that to, for example, another transform, or what's called strike slip earthquake that happened in Haiti about 10 years ago, or a little more than 10 years ago. And again, it was about a 7.0. By our standards, not very big. Haiti is stuck between two strike slip faults that separate the North American and the Caribbean plate. And in that case, again, a 7.0 occurred 10 miles from Port-au-Prince. And it is one of the deadliest disasters in history. Not a massive earthquake, but over 300,000 casualties, okay, that occurred here. And of course, this has nothing to do with plate tectonics or the earthquake, but from infrastructure. And we always say this in our classes, it's always the buildings that kill people, okay? It may, we can talk about how giant and destructive, or how destructive giant earthquakes are, but it also depends upon the economy and the infrastructure. So the largest earthquakes occur at these subduction zones, okay? So all around the Pacific especially, okay, where the Pacific plate is sort of diving underneath the Aleutians and through Japan, okay? We've gotten sort of the biggest, sort of megathrust earthquakes. And these are just some examples, and this is a plot of the 20 biggest recorded earthquakes from about 1906 to now. Okay, you can see they all occur in this ring around the Pacific. Sort of a cartoon example of the Pacific. Again, it's moving forward about roughly 10 centimeters a year off towards the North Pacific, okay, colliding into these other plates, Eurasia, and this part here is where the Indian or Austro-Indian plate is diving underneath the Pacific plate, so it's an interesting zone here. Okay, and this whole area is often termed the Ring of Fire. Well, the Ring of Fire really refers more to the amount of volcanism that occurs all around it, but I think people also sort of equate it with earthquake activity as well. So a massive amount, or most of the sort of the seismic activity really occurs here around the Pacific. So when seismologists want to do things like use a sound waves to image the inside of the Earth, they don't have a choice of where those sound sources are coming from. Most of them are really coming from the Western Pacific. Well, subduction zones are often tsunamigenic. Okay, I'm going to have to play this movie a couple of times. So what you're seeing here is this subduction zone. Here, before I give it all away. Oh yeah, okay, whatever. Okay, so let's see if I can pause this. Okay, pause. Oh, nope. No, that's, can never get these to work right. Okay, so here, let's just stop right there, and then I'll move this forward. Here we go. So you have this big subducting plate grinding down or sinking down underneath this overriding plate, and as you see it go down, you'll see this overriding plate be bent, and it's basically being cocked like a bow of an arrow or crossbow. So it's being bent down, and you see it continue to bend down and bulge, and you see it'll turn red, and red is supposed to represent the amount of stress. It's not temperature, it's just how much stress is building up on that plate, and eventually that stress is too big for the frictional contact between these plates to withstand it, and eventually slides and snaps. Okay, and when it snaps, this downward bending pops up just as if you were releasing a crossbow or a bow and arrow. Let's see if we can get this to go. There we go. So you see it bending down, okay, and it's getting red because it's high stress, pops up, and that hoisting up of that column of water where the plate rebounds can wind up sending out these ripples of water, which are these tsunami. Out in the middle of the ocean, the tsunami are almost unnoticeable. If you're on a boat, they're probably a few centimeters high, okay? They travel incredibly fast, but when they wind up coming up on shore, they wind up causing, I mean, we sometimes have this image of tsunamis being this beautiful breaking wave, someone's going to surf, but they're not like that. You'll see some images of that later. So just a few examples quickly. This is actually not one of the biggest earthquakes that occurred. I bring this up for historical reasons. The Alaska earthquake in 1946 was really about an 8.6, magnitude 8.6. There were two large subduction zone earthquakes that wound up causing a tsunami that, of course, ran up onto Alaska immediately. There was no time to do anything about it. But just to show you the power of the tsunami, this is what's called the Scotch Gap Lighthouse, which, as you can see, is this big cement structure. And after the tsunami hit, there was no one around to see how big it really was. That's what was left of it, basically nothing. Okay, it was completely wiped out, and there were a few workmen in there that were killed. That tsunami then ran off and spread across the Pacific, and after, usually it takes about 5 hours or so to get across the Pacific, and it wound up running up into Hilo and causing the tsunami. And this is one of the very famous pictures of people running away from this big bore of white water coming in from the tsunami through the streets of Hilo. That wind up causing, significant fatalities, and this is what wound up leading to the development of the Pacific and the Alaska tsunami warning centers, which now people use to try to predict or to forecast when a tsunami is coming. And you've heard about it in the news off and on. Okay, there are a lot of them I could talk about, but probably one of the biggest disasters that we have in history from 2004 was the Sumatra Andaman earthquake and the Indian Ocean tsunami. That had a lot of stories behind it because there was no warning system in the Indian Ocean that was useful enough to basically predict whether a tsunami was happening. And so, at the time, my former postdoc was actually the deputy director of the Tsunami Warning Center, was on call when that tsunami happened, so I got a lot of firsthand phone calls and texts at the time it was even going on. So it was about a 1,200-kilometer long rupture, which is enormous. It took 7 minutes for it to rip through the crust. Okay, and the first estimates of the magnitude of it were low. We're in the high 8, so it wasn't clear whether it would generate anything like a tsunami. It was much later that estimates were moved up to about a 9.1, 9.3 as an upper estimate. Okay, and it happened about 30 kilometers below the seafloor, caused a lot of uplift, and this wound up leading to a lot of casualties all along the Indian Ocean, through Thailand, Sri Lanka, India, and all the way over into East Africa. This is sort of a computer simulation by Satake showing this, the ripples of this spreading across the Indian Ocean. And one of the effects you can see is where it's deep water, it moves very fast. The tsunamis will move about as fast as a jet plane flies. Okay, so it will take, you say it takes 6 hours to get across the Pacific. That's fast. It would take you about that long to fly in a jet airplane across the Pacific. Coming up to Thailand, okay, the water is shallower, so it moves more slowly. So by the time the first reports came in that Thailand was being hit by a tsunami, they knew that India and Sri Lanka was already being hit. These were people working in the warning center, so the best they could do is warn people in East Africa. And it was really a terrible disaster. But as an example of the power of this, Banda Aceh, which continues to be sort of the ground zero for continuing earthquakes in this region, this is an example of sort of a neighborhood of Banda Aceh before and after. You could see that it was just erased. Okay, well, this has happened several more times even since this earthquake has happened. So it's just for practical knowledge. I always tell my students this as well. Okay, if those of you who go on vacation to Bali sometime and you see the water run out, okay, don't run out after it, please. Okay. Oh, I mean, these people do that. This happened, and the deaths that happened in Hilo in the first earthquake, that's exactly what happened. The water ran out. They went out to go collect starfish and shells and say, how cool is this? Like I'm walking on the bottom of the ocean. Okay, but that's just a tsunami. That's part of the tsunami. It's the trough of the tsunami that comes in first, and then when the crest then follows, and sometimes there are 2, 3, 5 crests that will come in. It's not one tsunami. So these people in Thailand wandered off, and they were caught, okay, in the crest of the tsunami that came in after the trough. So, several things you can always watch out for when you are on vacation in an area of this world. One is, don't trace the wave out, for God's sake, okay? If you see water lapping up in your swimming pool in your hotel, that's a bad sign. Also, if you see ground shaking going on, lamppost shaking, and they're going on for a long time, okay, the length of time of the shaking event is usually a good indicator of the size of the event. So if it's going on for minutes, that's probably a sign that a big earthquake is occurring. Just to point out, just about a month ago, there was this earthquake, a magnitude 7.5, that also wound up causing a tsunami in Indonesia, in Sulawesi. It happened very close to the city of Palu, okay? And so these are some examples of sort of the tsunami run-up that caused damage to this mosque. Some other images you would have seen were not really due to a tsunami, it was due to liquefaction. The shaking of the ground caused basically the ground to turn to liquid. So it's called liquefaction, and things just would sink into the ground and become unstable. So a lot of damage was caused by that as well. So again, just a month ago, okay, there was this event that caused a loss of about 2,000 lives. Anyway, so you saw that in the news. Okay, so let's jump to volcanoes. I know I'm blasting through this at high speed. Let's see if I can actually finish this. This is actually an image of the eruption of Montserrat in 2010 that occurred about a week after I was there, but okay. Well, too bad I missed it. But so like earthquakes, volcanoes occur mostly on plate boundaries, not all of them. There's some very famous ones, which we'll talk about, for example, Hawaii. But the magma and the eruption style also depends upon the plate boundary. So the one message that I hope you got from the last bit is that subduction zone environments are where the really big earthquakes occur, okay? Well, it turns out it's the same punchline here too, okay? The really explosive damaging earthquakes also happen to be where subduction zones occur. All right, so we'll get to that in a bit. But it has to do with how the magma is formed. All right, so first of all, if we look at mid-ocean ridge magmas, and I don't have sound plugged in, but you'll probably hear it out of my laptop in a minute anyway, it draws mass from the mantle. So as these two plates pull apart, the mantle has to fill in the gap, and as it rises up, I wouldn't worry about it, Jean. You'll hear a grumbling out of my laptop. It's okay. Or I'll make the noise with it. Okay. So it draws mass from the mantle, it rises up, and when the pressure is released, it becomes easier for it to melt, and some of the mantle then melts on the way up. And when it comes up, this melt is, it's basically some section of melted mantle. It's pretty rich in metals, okay, combined with silica. And silica, when I say silica, it's things like glass or quartz. Okay, but you mix enough metals with this, and it will keep the molecules, if it's small, they'll roll over each other. It will make a thin, runny magma like you will see often happening in images of lava flows in Hawaii, okay? But at the, well, I'll say this, okay, as you're watching this movie, most of the volcanism, most of the magma production on the planet happens at these mid-ocean ridges where plates are pulling apart. But it's not damaging, it's not, it's at the bottom of the ocean, and it basically just oozes out. Okay, and usually it comes out of these sort of pillow basalts, and you can see these sort of basalts flowing out and running downhill, okay, and forming look like these snake-like, creatures, but it's just flowing out, freezing, and when eventually gets a crack, and then you'll see it sort of flow out again through another crack, and at some point you're going to see this courageous guy with his scuba diving fin right next to it. It makes you wonder, what is wrong? Oh, there he is. Look at this. He's like, okay. That water is boiling right next to it, so I doubt he had to keep that fin afterwards. Okay, so this is the least explosive and dangerous, but is again where most magma is produced. Non-plate tectonic volcanoes, okay, for example, Hawaii is the classic example, and since I lived there, I've got like endless stories to tell about it, but I'll try to keep them fast, okay? So these are intraplate volcanoes. Hawaii is smack in the middle of the Pacific plate, very far away from any plate boundary, and it's thought to be caused by a hot jet or hot plume of the mantle rising up, perhaps from the core mantle boundary, and eventually being hot enough to burn a hole through the strong part of the mantle and through the crust, strong part of the mantle we call the lithosphere. It burns a hole through it, causes melting and volcanic activity as that plate moves off to the northwest, okay, leaving this trace of islands behind it. And it's one of the ways we think we understand the direction of plate motion, okay, from that, okay. Don't have a lot of time to go into that, but at least we can talk about these lavas, okay. So these are very thin, runny lavas. They flow all over the floor, all over the ground. This is me 10 years ago. People always think I'm barbecuing chicken, okay. That would be disgusting chicken. I mean, this stuff smells terrible when it's burning. But you know, you can poke a stick into it and you can play with lava, and it's always a gas, okay, unless you're terrified of it, okay. But these hotspot settings wind up leading to these very runny lavas. You get rivers of lava. When they're first releasing gas, they create these fire fountains and fire sheets that look like they're enormous. They're actually not that big relative to other volcanic eruptions, okay, but they're spectacular, okay. When I moved there, not long after I graduated from here, I did a postdoc, then I moved to Hawaii for my first faculty position, and when I arrived there, the Kalapana coast, which is now where one of the big eruptions was going on earlier this year, and still ongoing, okay, was happening. This Kalapana coast is being destroyed then. Now it's just all black, but back then there were golf courses and other communities, and you saw this lava flow flowing all over it. But just a quick example of how quickly it flows. Sometimes when I've gone out into these areas to play in lava flows, in an hour you can't recognize the landscape because so many of the divots in the valleys have filled up with lava. So here we are in April of 1990. There was this little mom and pop shop, okay, in Kalapana. You can drive all over the big island and find these. Sometimes they call crack seed shops, okay, it sounds bad, but it's just candy, okay. And eventually the lava flows would, by June, actually filled up to the point of destroying this. And this is June 6th, June 13th, a week later, the lava was basically up to the base of that sign, okay? So that's how quickly this would fill up. And the volume of lava being produced is massive when these things are flowing. In 2018, just recently, okay, and still ongoing, there was this major rifting event, okay, that happened right to the Leilani Estates in the same region. And we were there, and where I was poking lava with a stick was in the same region 10 years ago. So earlier this year, you saw this rifting it right through this neighborhood, and these lava fountains and sheets coming out and causing a lot of destruction, as Jean-Luc pointed out earlier. Okay, so a lot of evacuations from this event. Quickly, we saw 8 years ago this huge. Well, Eyjafjallajökull is not a big event. I mean, it's a small volcano. This is Iceland, and it sits right on top of the Mid-Atlantic Ridge, which then cuts down through here. We were talking earlier today about Thingvellir, where you, in principle, can put your foot on either side of a tectonic plate. But most of the volcanic activity happens on this other branch of this rift that comes through Iceland, and Eyjafjallajökull is way down here next to a much bigger volcano, Katla, and bigger volcanoes up here called Krafla, and these are much more potentially damaging. But at the time this erupted, there were first lava flows, then glacial water got into the lava flows that caused these sort of these splintering glassy ash eruptions. And unluckily, Iceland happens to sit right underneath the jet stream, and this ash plume was lofted right up into the jet stream, which sits pretty low down over Iceland, which is then carried over to Europe and caused a lot of damage to airplanes and cancellation of flights and a lot of economic damage through various parts of Europe and England and Iceland. Everybody always has to ask about Yellowstone. I used to give this talk, and if I forgot about Yellowstone, someone's going to say, what about Yellowstone? Anyway, no, okay. Well, Yellowstone is the biggest volcanic field in the U.S. And I went there last summer. Honestly, it's a lot of steam. Okay, I mean, it's massive, and the potential for it to cause damage is very large. But people get worked up over it, and I think sometimes for misinformation. Probably most of the frequent eruptions are steam eruptions. They're less frequent lava flows. What people think of as the super volcano that's going to destroy the world. Okay. Though there have been big caldera eruptions, when you have a big eruption, the magma chamber empties and then it collapses, then it can wind up spewing out a lot of lava and ash and other things, and it would be enormous if it happened. Okay, but it's something that happens on about a 2 million year recurrence interval, or about maybe 1 million years if you want to be generous. 1 million years doesn't mean it's going to happen now, any day now, because a million years have gone by. All it means is you have a 1 in a million chance of it happening in any given year. Okay, I mean, the probability does accumulate, okay, but it doesn't mean, it's like clockwork, right? So there's a very good website. There's the USGS Volcano Observatory in Yellowstone, sometimes called the YVO, Yellowstone Volcanological Observatory, and they have a nice description of, in their FAQs about misconceptions about the Yellowstone eruption. So, I always get the question about, are we going to all be killed any day now by, and answer is no, not yet. Okay, but the big volcanoes, the more destructive volcanoes are the subduction zone volcanoes. Okay, try to keep track of some time here. Again, okay, that was part of the main message. Subduction zones are the killer. Okay, I mean that's an overstatement, but they're also some of the more fascinating parts of what we study about the mantle and plates. Again, most of them occur around the Ring of Fire, and the types of volcanoes that occur are really unique to this planet. I do not think we see, maybe Jerry might disagree, maybe, I don't know. But, okay, he's not trying to, okay, he's just shaking his head at me. Okay, about whether or not we would see this type of volcanism on other planets. As far as we know, this is very unique to the Earth, and it's a bit complicated, so just bear with me a little bit, okay? Is that a subduction zone or basically a tectonic plate, because most of the time it's sitting at the bottom of the ocean, the minerals in the crust, and even somewhere down, deeper under the crust, get hydrated. They become hydrated minerals. Ones that you're used to thinking about are like talcum powder or asbestos. That's not what's happening at the bottom of the ocean. They're more things like serpentine, but minerals that become hydrated, and they get drawn down into the mantle, okay? And they eventually reach temperatures and pressures where those minerals aren't stable. They can't survive at those temperatures and pressures, so they release their water. That water diffuses or kind of gurgles up into the mantle above it, and when that wets the mantle above it, it makes that mantle easier to melt. It doesn't mean that it's hotter. It just means it's easier to melt, so it undergoes some melting. Then that melt then gurgles up through the overlying crust, and when it first rises up, it's the same type of magma, other than being a little bit wet, as what's coming up, say, for example, through Hawaii or through a mid-ocean ridge. It's just what we call basaltic magma. Okay? It's runny magma. But as it rises up, it not being a particularly hot melt, it's a cool melt, coolish, okay, that it winds up melting stuff that's easiest to melt. Right? The stuff that's easiest to melt in its way turns out to be rock that is rich in silica, and again, silicon dioxide, it's like glass or quartz, okay? That's the end member, okay? But any sort of rock that's rich in that is easier to melt, and so it becomes contaminated in this silica-rich stuff, and by the time it gets to the surface, it's a magma that is rich in silica, and silica-rich magma tend to make really gooey magmas, magma that's like bread dough, very long molecules that get tangled up with each other and become very difficult to move. So that magma is thick and pasty, and it plugs up the volcano. It hangs on to the gas that is formed because it's coming out. Remember, the water is coming out, and actually CO2 also. It hangs onto the gas as it plugs up the volcano, builds up enough pressure, and this is usually what causes these explosive eruptions. They're not, I mean, sometimes if they're hot enough or there's enough basalt in them, they may be runny, but a lot of times they just look like this big, ugly pile, okay? Whatever, okay. But again, they kind of come up as this pasty magma that just sort of gets stuck, and eventually it can build up enough pressure to lead to explosive eruptions. There are all these different kinds of eruptions that we can categorize, but I'll just touch on a few. So the one thing we often see with these volcanoes is they often wind up leading to things that look very different than Hawaii. If you go to Hawaii and you stand on the Big Island, you can't even see the volcano. It's so flat. Okay, it's so broad and flat. It's a shield volcano. You can barely even see where Mauna Kea or Mauna Loa are unless you're basically driving up to it. But these other ones make these steep-sided stratovolcanoes. If you want to think of it that the magma that's creating them is so pasty, it piles up to significant height before it starts to spread outwards. Okay, that's an oversimplification, but it's not so bad. All right, so it builds up these steep-sided stratovolcanoes that have this sort of classic conic shape to them. The most explosive versions of these volcanoes are these Plinian eruptions. Okay, there are different. There's Volcanian eruptions and caldera ones, which are big but rarer. But the ones we often see, for example, Pinatubo, 1991, and there's volcanoes. This has happened in the Kuril Islands, Sarachev Peak, and you can see examples of these, and I'll show more of them as I go along, that wind up blasting out gas and ash at very high speeds, up to 600 kilometers a second. Okay, they come blasting out, sometimes so fast. Well, they're usually going at supersonic speeds and cause shock waves that blow holes through the cloud deck. They sometimes are lofted 20, 30, maybe as much as 40 or 50 kilometers up into the atmosphere, reaching all the way up into the stratosphere. Pinatubo launched so much ash into the stratosphere, caused a global cooling event from aerosols that were formed in the stratosphere and caused reflection of sunlight. And so these are sort of the real big monster type eruptions. And when this ash column, here I'll go back one, it rises up, of course it's full of ash and it's rising because it's coming out fast and it's hot. But once it cools off, it's heavy ash and it collapses. So if you imagine this thing is, these are high mountains in the Philippines, so this thing is launching, already in the process of launching tens of kilometers above it. And when it gets cold enough and starts to sink and collapse, then of course it's going to collapse at very high speed. And these are often called pyroclastic flows. There are other ways a pyroclastic flow can occur, the collapse of a side of a mountain, but oftentimes these collapse of these big eruption columns will cause a very rapid ground flow or ground-hugging flow called this pyroclastic flow, something called a nuée ardente, which means glowing cloud, because they would glow at night. And they will travel up to 300 kilometers an hour, which this truck is certainly not going 300 kilometers an hour, okay? As morbid as that is, all right? But these are sort of some of the bigger hazards and killers that come out of these types of explosive volcanoes. Again, to back up, because the magma is gooey and plugs up, it builds up a lot of pressure, okay, because it plugs up the volcano, and eventually when it does erupt, it does so by exploding outwards and leading to these events. So a few historical examples, and then we'll move on to other things, okay? Don't want to keep you here too long. Is, of course, I mentioned the Plinian eruption is named after Pliny the Younger for having observed this eruption in 79 CE that wind up causing the destruction of Pompeii from pyroclastic flows, and lahars, which are a mixture of ash and water. Herculaneum was also destroyed by pyroclastic flows and lahars. And these eruptions actually continued onwards, but we also, you can go to Pompeii and find, these humans and dogs and others encased in ash under low oxidizing environments, so they're still preserved. It's sort of the great tourist volcano. Tambora, again, I'm just giving you a quick sample, is probably thought to have been the most powerful eruption recorded, okay, in history. And this wound up causing these two Plinian eruptions that went 43 kilometers up into the atmosphere, up into the stratosphere. The pyroclastic flows killed 10,000, destroyed 2 kingdoms, wind up causing hundreds of thousands of fatality and famine from destroying crops, in other words, and fields around it. And then it also wound up causing a year without a summer in 1816. And it's thought actually that Mary Shelley wrote Frankenstein during this year because it was a horrible wintry year, and she and her colleagues were sitting inside thinking of horror stories to write for each other. I think that's completely anecdotal. Who knows? Maybe they were just a bad week. Who knows? One of my other historically favorite stories is of the eruption of Montpellier in Martinique. And this is thought sometimes to have been sort of the birth of modern volcanology, of trying to really understand the difference between volcanoes. Okay, because at this time, one of the reasons, well, here, I'll tell you the story first of this, is that It's quite famous for what's called a direct blast pyroclastic flow. I'll explain what that is in a second. But what's interesting, this is also interesting for historical and political reasons, is that the indications for the eruption was actually not a big surprise. This was happening for 6 weeks or more beforehand. This entire community was being inundated by ash. There were already loss of lives from a lahar, a mud flow destroying a sugar factory. There were bizarre events happening because of the ash flows. Some of it is probably apocryphal, but it sounds great. For example, it's thought that pit vipers, snakes, were driven into the city of Saint-Pierre and killed several people until feral cats came out of the alleys and attacked the snakes. And you can imagine the scene of the snakes versus the cats. It sounds like, snakes on a plane, but it's snakes in the city with cats. Not as good a movie, but okay. But what's more interesting about it is that one of the reasons it caused such loss of life is because there was an election going on between two parties. One was sort of the landowners conservative party, and the other was sort of an upstart Creole party. And they were running an election for the control of the island, but they but neither one of them wanted the city of Saint-Pierre to be evacuated because Saint-Pierre was the capital of Martinique. Okay, so they refused to allow evacuations. The governor actually put guards on the exit to Saint-Pierre and would not let people evacuate. And they encouraged people to actually move into the city itself because they argued that it would be safer since it was surrounded by these valleys that separated it from the volcano itself, because they thought that it would be just like a Hawaiian flow and had these runny lavas that would come down and be trapped in the valleys around it and would never be sort of routed around the city. But in the end, what happened is on May 8th, there was a lake on the top of the volcano that collapsed and basically caused the volcanic eruption to shoot sideways directly at the city of Saint-Pierre. Within seconds, it incinerated the entire town and left it like this, okay? And there's this sort of story that there was one survivor who was lying at the bottom of a prison cell, and then, it's probably not true that there were probably other survivors, but he was hired by Barnum and Bailey as like a freak show character to tell the story of how he was on death row and saved by the volcano, but he was probably there for petty theft, okay, and being drunk and disorderly. But anyway, so it's a fascinating story. That I've been there a few times. We've taken students, so this is some photographs we've taken. You can go inside Saint-Pierre and to the dome inside of it that was built within, like, it was a big dome built from that eruption that happened, built in about a year, okay, which is fascinating to crawl around on. Recently, there was this volcanic eruption, Volcán de Fuego, one of the bigger volcanoes in Guatemala, that caused, had several eruptions, pyroclastic flows, and several fatalities. And one of the tragic stories of this is, my family is sitting over here, where their older daughter lives in Guatemala and was showing images of people with their iPhones taking pictures of the pyroclastic flows coming into their village because they didn't realize they would move that fast. And those images that you might have seen of Volcán de Fuego were people that were then killed shortly thereafter because they didn't understand the pyroclastic flows were going to wipe out their village. Quickly going through this, one of our more famous volcanoes, for those who were around in the 1980, I was actually driving through this area when I was in college, when Mount St. Helens erupted. And in a way, sort of like Montpellier and Martinique, it actually underwent a flank collapse that caused an early eruption of the volcano that caused sort of a sideways. It didn't shoot sideways, but it wound up shooting an angled eruption outwards. And a 20-kilometer high eruption, it basically destroyed all the forests around it. There was enough time to evacuate most people, except for those who refused to be evacuated. And then there was dome regrowth around the mid-2000s or so. I have to show this picture. There's my daughter, Hannah, who in her before her freshman year was taken up on a field trip. So as you were talking about the importance of field trips, was taken up on a field trip and hiked to the top of Mount St. Helens, and there behind her is the flank collapse. And there is the regrown dome behind her. Too dangerous to go down in there. There she is for scale. Okay, well, she's nodding. And just so my other daughter doesn't get annoyed with me, I'll show her. There she was in Antarctica, but it has nothing to do with this talk. Okay. Okay. Just so I told her I showed that too. She doesn't get it. Okay. Let me just fill. How am I doing on time? What do you want to tell me? 2 minutes? 3 minutes. Okay. that's 3 minutes, but in some sort of relativistic time where I can, okay. I will just talk a little bit about a couple of other issues, okay, which is the importance, we talked a lot about earthquakes and volcanoes, but there's sort of, since about the early 1980s, there is this growing theory that plate tectonics is largely responsible for why our climate is habitable and stable, okay? So the idea was that because of the continuously exposed new minerals that come about from volcanism, from opening up of plate boundaries, from building of mountains and collision zones, the minerals that are constantly freshly exposed to the atmosphere, and especially to rain, okay, basically washing over, so rain tends to actually be precipitated in mountain ranges, okay, would cause weathering and erosion of these minerals. And a lot of times because the rain has dissolved carbon in it, and it's basically like it's carbonic acid, which is what you drink when you're drinking Coca-Cola, okay? That carbonic acid would wash over these minerals, react with them, and make carbonates, okay? And those carbonates would eventually wash into the ocean and eventually wind up in continental, in crust, okay? And this is basically where almost all the original CO2 of the planet is that we started with, which is not so different than Venus's thick CO2 atmosphere, is now bound up in rocks, now mostly limestone, but other ones like dolomites, okay, because of these fresh minerals reacting with CO2 through water, through the hydrologic cycle, sucking out the CO2 of the atmosphere, locking it up in rocks, okay, and therefore, you know, our atmosphere is now mostly nitrogen with oxygen in it, not CO2. If it wasn't for this, it would be mostly CO2, a very thick CO2 atmosphere, about 60 atmospheres or so. Okay, but what's important about stabilizing the climate is that there are two different groups that propose that this gave what's called a negative feedback that would keep the climate stable. And the way it works is this, is that if for some reason you wind up having a cooling event or you don't have enough CO2 to generate a greenhouse gas atmosphere to keep things warm enough, it gets too cool, okay, that would reduce the amount of rainfall because you're only going to get rain if you evaporate seawater and make clouds, okay, so it would reduce the amount of precipitation and weathering. And the lower temperature would also reduce the rate of reaction of creating these carbonates, okay, with this acidy water. Okay, so you would, by two mechanisms, reduce the amount of drawdown of CO2. So if things got cool, you wouldn't suck down CO2 as well. And meanwhile, the volcanoes would continue to spew out CO2, okay, from these arc volcanoes and from mid-ocean ridges and rebuild the CO2 back up again. So if you cause a cooling event, okay, you would stop drawing down CO2, and then the CO2 would build that back up again and get things warmer. If it gets too warm, it goes the other way. You get more precipitation and faster reaction of CO2, okay, and therefore it would draw the CO2 down faster. So if it gets too much CO2, it sucks it back down. If it's too little CO2, the CO2 gets built back up. And this is sort of a very important theory about how the Earth's climate is stabilized because of all this geological activity on our planet. This doesn't happen overnight. It's something that happens over tens of millions of years, right? So that stabilization is something that is not going to save us anytime soon from burning up all of our fossil fuels, okay, unless we accelerate this activity, okay? But it is something that stabilizes the climate of the planet over 10 million years, which we think is responsible for keeping things stable enough that animal life form, complex life could form. Okay? Otherwise, we would just be a bunch of bacteria listening to an archaea lecturing to you about plate tectonics, okay? Maybe. I'll go the archaea. It's probably the other way around. Okay, but like archaea jokes. Okay. The other idea is that at the bottom of plate tectonics, and then I'm going to stop. Okay, I promise. I'm somewhere still at 2 minutes right now. I promise. This is it. Okay. It possibly provided the first energy and nutrient source for life on the planet when it's, you know, we think life goes back at least 3.5 billion years, maybe 3.8. Okay. And during that time, it's thought the planet might have been sort of a very hostile environment in terms of a lot of bombardments from asteroid objects. Okay, there's a period of time called the late heavy bombardment where it's thought that a lot of material from the outer solar system was being flushed into the inner solar system. And it's thought to have perhaps been a hostile environment for life to form on the surface. So in 1977, it was discovered by the Alvin submersible, so a research group off the Galapagos Islands, the Galapagos Spreading Center. They found these black smokers of these undersea hydrothermal vents spewing out. Let's see, this actually has a movie to it. Okay, these black smokers spewing out this nutrient-loaded, hot water, boiling, super boiling water. It was at the bottom of the ocean, loaded with things like hydrogen sulfide and other minerals. And around it, they found these entire communities of tube worms, okay, that were living off of biological matter that was generated by not bacteria, archaea, okay, which are different than bacteria. At the time, they didn't know that, but now they're called archaea and called thermophiles, things that can live in super hot water, and they only like to live in hot water, but they were living off of the nutrients and the energy source coming out of these volcanoes. So that sort of completely revolutionized the idea about where might life have started, not from photosynthetic reactions, that is from sunlight, but from chemosynthetic reactions, from the drawing of energy and chemicals from plate tectonic environment, for example, at mid-ocean ridges from the volcanic activity. At that point, I'll just close with this, and there is other stuff I could have showed you, but that's fine. This is good enough. But one of the things that we'll just point out is that the Earth seems to be quite unique, okay? And there are this occurrence of plate tectonics and liquid water and a temperate climate and life, right? And it's not that they're coincidental with each other. Probably a lot of it is due to the presence of plate tectonics providing a continuously active geologic environment and exposure of minerals to draw down CO2 and provide nutrients for life, and of course also causing earthquakes and volcanoes, okay? And so it always becomes important to try to understand why we have plate tectonics, okay, and what are the reasons that it might arise on our planet, and whether we can expect it to arise on planets. Well, probably not in our solar system, but maybe, okay, but certainly when we start to explore and discover planets in other solar systems. It's one of the things that I study. I don't have time to show it to you just as well. It's like a lot of equations. No, I'm kidding. Not really. But okay. But at that point, I'll stop, and we'll be happy to take questions. Okay. Thank you. What's that? Yeah, sure.
I will ask our panelists to join us to the front. And while we're doing that, if you have questions for a speaker, please write them on an index card, and our volunteers will collect them. And then please take a seat. Yeah, I'll have Dave here in the center.
I'm a panelist too?
Yes, you are.
Okay.
Please have a seat.
Oh, I thought you could lift me off the hook. No.
So,
microphone is on.
First of all, thank you, Dave, for a truly wonderful talk. I think it gives new meaning to our mission of understanding and protecting our home in the universe. I want to ask you about a memory or anecdote about your time at UCLA.
Oh, my God. Okay. Well, I mean, I'll say one thing. I mean, I will, for those you students of you, I mean, we'll have to confess that I was probably one of the worst students in the class that was admitted that year. And, but to, a lot of people's credit, and especially to Jerry Schubert, who continued to encourage me to give it a shot, I probably eventually grew up enough to get out and to graduate. And so sort of my fondest memory is the fact that Jerry and others in the department were, supportive of my continuing to try and giving some poor dumb football player a chance to my brother's laughing at me, of course, but okay, to try to make good. And so, I greatly appreciate that. But on the other hand, a less serious note is that in Jerry's lab, in his office, I think that one of my closer friends who was actually studying tidal heating on Io, Jerry didn't never know this, but we were oftentimes just screwing off in the lab. I know that's just, and two of our favorite things to do is to play with water rockets. Anybody remember water rockets? You pump up the water and blast them. Yeah, we did a lot of that, and I think we hit a few windows on the outside of the building. And I think John Wasson, we smacked his window and he got mad at us. And we also had a lot of played a lot of silly putty. Okay, I won't say what we did with it, but okay. So somehow or other, we still graduated, and I think Jerry knew what we were doing all the time. But those were some of my fonder memories.
Thank you. So I want to introduce our panel speakers. We have an undergraduate student, Christina Kitamikado, and then a graduate student, Abijah Simon. And on my right is Professor Lingson Meng, an assistant professor in our department, and Professor Carolina Lithgow-Bertolini. So I'll ask the first question to our undergraduate student, because you experienced this active volcano in Hawaii, and so as part of the field trip, how did it feel?
I would want to say, yes, it was a wonderful vacation, but it wasn't, because I did a lot of work, which is great. I had an experience before that. I got to go to Hawaii over the summer, and that was a geological kind of aspect of Hawaii on the Big Island, but this time with my class, with actually Professor Paul Davis, who's sitting over there. He led us to do a lot of geophysical experiments there, and it was wonderful. So I got to see Hawaii in a geological sense and a geophysical sense. So it was really great to have that experience, yeah.
Can you describe some of the measurements that you took while you were there?
Sure, we took a lot of geophysical data for the geophysical class. We took gravity measurements, magnetic, self-potential, and VLF, which stands for very low frequency. And it's a real measurement, I promise. It doesn't sound real, but it is. And we compared those to a lot of the data that was already collected by the USGS, which is a government-based geological survey group. And we also compared our data to how we can apply that to other planets, for instance, like Mars. So we compared our data from, the volcanoes that we looked at in Hawaii to, for instance, like Olympus Mons. And it was a really interesting find, because we can explain some of the things that were going on in Hawaii to the same as in Mars. So that was really interesting.
All right. And then in terms of the field experience versus your classroom experience, do you have anything to say there about the relative merits of each? Or?
Yeah, it's definitely important to know the theory, but it's also great to see it in person, because then you're like, okay, it's not just perfect, and you don't just get it handed to you. You have to work for your data, and it's a really good, humbling experience, because you're like, oh, okay, this didn't work. What do we do now? And then the professor is like, okay, just think of something, and we're like, okay, we'll do that. And for instance, the day that we left for Hawaii, that day of, our professor said, oh, we didn't get enough data. We cut our line short, and so we have to go back out. And then so a lot of students were willing to go out, because that's what we were there for. And it was a great experience to know how data is really retrieved in the field. And I think it's a really important thing to do for students.
All right. Thank you. So Abijah, you study the manifestations of plate tectonics for your graduate work. Can you tell us briefly about your work and why you're passionate about it?
Okay, sure. So first of all, sorry in advance for my voice. I was on a field trip this past weekend for the class field mapping that I'm TAing, and I kind of lost it out there somewhere. But
the danger
yes,
of field work. That's right.
It is a day in field work. Yes, Dave would know a lot about it. So after that fantastic introduction to plate tectonics by Dave, I am also very interested in plate tectonics, and my main research area is in the Eastern Tibetan Plateau. So what I'm trying to research right now is what are the mechanisms and timing of uplift of this region. So you guys probably know about the Himalayan orogenic belt, which was caused by the collision between the Indian and Eurasian plates about 50 million years ago. And we're thinking that the uplift of the Eastern Tibetan Plateau is caused by a similar mechanism and by the same collisional event. So I'm using a combination of field mapping, seismic profile reflection, and thermochronology to try and constrain the mechanism of the uplift in this region. And why I really like this area, well, first of all, when you're out in the field and you have these giant steep mountains that are rising like 18,000 feet around you, you can't help but wonder, what are the mechanisms that created these mountains? Why are they here? How did they form? And not just that, they're so awe-inspiring, but kind of like what Dave was talking about with these regions having a lot of earthquakes. There was a 7.9 magnitude earthquake in 2008 in this region that affected millions of people and caused over 70,000 casualties. And because of this, it's been really a hot spot for tectonic research in this area, and I want to help to contribute to the research in this area and figure out why there's these earthquakes and what are the natural hazards of this region.
Excellent, thank you. So on top of your graduate work, you're also very interested in education and public outreach. So can you tell us about your efforts in this area?
Oh yeah, so well, this year I am one of the group coordinators for the event that John Luke introduced, which is called Exploring Your Universe. And this is a fantastic giant event that is actually put on by just a small group of students, including me. And we are going to have like maybe 40, 50 science booths by the STEM departments in UCLA. And it's a really family-friendly event, free to the public. Anyone can come. And we have all these interactive exhibits. EPSS this year is having 12 exhibits that covers everything from earthquakes, meteorites, Mars, and some of the satellite missions. So I would encourage everyone to come, and it is actually this Sunday from 12 to 5 p.m. If you're interested in this event, I would look up Exploring Your Universe or go to our website at exploringyouruniverse.org. And really, it's a fantastic event. I would encourage everyone to join.
Thank you. I want to ask Ling Sen about your large earthquakes. You study large earthquakes and tsunamis. Can you elaborate a little bit on their power and destructive power and their location? We've heard a lot about it.
Right. Yeah. I think Dave already gave up most of my answers in his talk. Yeah. So I'm a earthquake source seismologist. I study bigger earthquakes and interested in how these earthquakes starts and where do they propagate and what stops these earthquakes and what are the physical processes that drives these bigger earthquakes. The most destructive powers of all these natural disasters would no doubt be tsunamis, right? As what Davis points out, and that 2004 Sumatra earthquake that kills like 250,000 people, and that's the most deadly one. And for earthquake, that Haiti earthquake in 2010 has a comparable casualties. And that's really motivates all these studies for earthquake source. And we want to be able to one day understand the physics enough so that we can make better forecasts.
Yeah. So the early warning systems can presumably save lives in this context.
Right.
So what is the state of these systems in California?
So like early warning will be something very promising at the moment to actually significantly reduce these hazard. In California, I think we're doing really well. Recently, just in the fall of 2018, we start to have the phase 1 test of the shake alert system, which is what USGS and UC system and a few other institutions are developing. It went into the like kind of a public test. Right now, they are sending alert to some public agencies and major commercial entities like the train system or major medical centers. And in a couple of years, we're going to go out into phase 2, which is going to be open to the general public in California. Yeah.
And I think you have some ideas yourself about how to improve these early warning systems. Can you tell us about it?
Yeah, so that's kind of one of my research interests. So think about early warning. This is something you would like to know the magnitude and the location of the earthquake as soon as possible. So that's kind of the idea for the current system that's going on. But it turns out that's not enough, just knowing the magnitude. So we have to also know the extent. Like the earthquake doesn't just break one point on the fault. It breaks different places on the fault. We want to be able to map that in real time, because that's, even if it's the same magnitude earthquake, it affects the kind of places of strong shaking at the same time. So we want to kind of image this as a dynamic process in real time. And my idea is we can borrow a lot of these techniques developed in telecommunication communities where they use antennas to track airplanes, vehicles, or cell phones using cell phone towers. So we want to use those tracking techniques, but apply it to seismology as we're studying wave propagation problems. And if we can do that in real time, that's not only going to tell you the magnitude, probably also going to tell you one thing is very important is where this thing propagates. Because if you are facing the earthquake, you can expect a much stronger shaking, even if it's the same magnitude.
Thank you. So Carolina, you're building a lab in a building. You just arrived a few months ago, and that lab, I understand, is going to involve tons of maple syrup. Can you
corn syrup, but it's because I'm so sweet, right? So actually, this relates to what Dave was showing, which is the volcanoes that don't happen at plate boundaries, but the volcanoes that are like Hawaii, not on a plate boundary, and so they are more difficult to understand because they're not as easy to relate to the mantle convection system in terms of the subduction zones or the ridges. And so the idea is that by experimentally looking at how these hot jets are formed and they come to the surface and what deformation they may cause, that you have a better understanding on how they relate to the whole plate tectonic mantle convection cycle. Now, the first question you should ask is, how could you possibly use corn syrup to study the hot jets? I'll let Dave answer that.
Oh, okay. Really gonna throw that at me? Okay. Well, well, first, it doesn't kill anybody. It's always the first rule of those experiments. Don't do something that will harm anyone. Right? Yeah. If you can eat it, then you can't do any harm. But no, but actually, it's a good question that we actually sometimes when people do laboratory experiments to understand how things flow, for example, in the ocean, in the atmosphere, in the mantle, that the mantle is probably the easiest one to do because although syrup is not as gooey as the mantle, so if we want to put a number on it, okay, so syrup has got what we call a viscosity of about 10, and the Earth's mantle is about 10 to the 21, okay? So that's 1 with 20, zeros after it as opposed to just 10, okay? So, but on the other hand, a tank of syrup is much smaller than the mantle. So if you sort of take the ratio of the thickness to the third power relative to how gooey the stuff is, it actually is it's a pretty good model of the mantle. And so that's why syrup winds up becoming a very good fluid for understanding the mantle. Syrup or thick silicone oil, but syrup is also nice that it softens up when you make it warm.
And it's cheap.
And it's cheap. And it's edible. Okay.
Right. And it tastes good.
All right, well, I can't wait to visit the lab.
You're all welcome to come visit the lab.
So you hold the Slichter Chair in Geosciences, which was endowed partly to increase diversity in the geosciences, so we're thrilled to have you. But I wonder about Louis Slichter's legacy. Can you describe some of his contributions that relate to what we heard today?
So I think two of them relate very directly to some of the things that Dave was talking about. One is he was a physicist, I think, by training, and from a distinguished family, I think, of mathematicians and physicists as well. And so he started in that direction, and I think he did some stuff that related more to sort of kind of engineering geophysics in some way. But then he wrote a very important paper on thermal transfer. So how does heat flow through the Earth? And Dave mentions this, and the role of convection in that heat transfer. So that's one very important paper he wrote. Another one, which also relates to Dave's talk, is that he used the largest earthquake at the time. Well, actually, the largest earthquake ever recorded was the 1960 earthquake in Chile, which you mentioned. I think you had in your slide as 9.5. It was huge. It caused the Earth to ring for 3 days. And that's when our instruments weren't as good as today. And he used that earthquake to study the interior, the structure of the Earth, some of which Dave showed in his talk, including the first sort of real proof that inside, below the mantle where the core is, there is a part of it that is actually solid, the inner core. And so he really had the first proof of that from, basically all the ringing that this huge earthquake happened, had. you mentioned 1,200 kilometers for the rupture of the 2004 Sumatra Andaman earthquake. This was comparable. I think this was 1,000 kilometers, even though it was a larger earthquake that happened. That's a difference.
I could ask the students to bring the audience questions. In the meantime, I'll ask Carolina. We stole you from another institution. Why did you come to UCLA?
But so my previous institution was called UCL, so I just need to try to okay, so there's one answer. Here's the other answer. I did my PhD at Berkeley, so had to compete. No, I think it was too good an opportunity to pass up the history of the department in terms of geophysics and planetary, the opportunities for intellectual stimulation and growth that it offers. It was just impossible to pass up. And so far, it's been a fantastic experience, and everybody has been very kind and very welcoming. And I hope it will continue after the lab is built and ants start trailing into the building.
Yeah. All right. People's shoes stick to the floor.
Yeah. Yes.
All right. Our first audience question is, what are the chances of an active tsunami or volcano in Southern California, or the chances of San Andreas movement? Who wants to take that?
Seismology.
So in terms of the possibility of having a large earthquake on San Andreas Fault, that's, I think, very likely. And I think the estimate of a magnitude 7.5 plus earthquake on San Andreas Fault is exceeding 60% in the next 30 years. But there's, Dave Jackson would say there's a lot of uncertainties with that, because it's, so the last event that we have on the Southern California part of the San Andreas Fault is 1857. And based on the paleo record, people are being able to trenching along the faults and find out the bigger earthquake the last 1,000 years, the average interval between these large events is about 150 years. So that's one of the that's why people say the big earthquake in Southern California is overdue, right? Yeah, but this time can be very irregular also. So in terms of the tsunami hazard in Southern California, we don't live in the subduction zone, so we don't have those really big tsunami as in Indonesia or Japan. But some of the smaller faults offshore in Ventura and Santa Barbara has this potential to generate large thrust earthquakes that give locally large tsunami, maybe up to a few meters. This has been documented in some of the tsunami deposit, where it's really kind of the sand on the beach being washed to further inland. So there are some kind of geological record for that. So that's probably the scenarios for tsunami and earthquake. Volcanoes, I just don't know if there's any active ones here. Probably not.
Well, there's volcanic activity from these pull-apart basins, where
right.
San Andreas Fault is basically opening up some rift zones.
Yeah. Okay.
But you have to go to far northern California,
right,
to Mount Shasta, to get into the sort of subduction environment. Right. Yeah. But other than that, yeah, you're right.
Next question. Is it possible to predict the future movement of continents?
Yes.
Yes. Okay.
Yeah, that's not a problem. We don't expect it to change so fast the direction of motion that we couldn't predict a few million years into the future. That should not be a problem.
All right.
Yeah, a few million years. A few million years is small enough.
Yeah.
A few million or a few tens of million.
Yeah, still small.
A few million.
All right. Is plate tectonics pretty well understood now, or are more discoveries imminent?
Well, I would say hopefully there's more discoveries imminent, or I'm out of a job. No, I think that what we understand about plate tectonics in terms of having mapped out its motion. Okay, that is pretty well understood, but even there are large parts of it that are not understood. We see areas that are sort of don't fit into the plate tectonic model. For example, in the middle of the Indian plate, okay, there are areas where there is a lot of deformation of that plate that is distinctly non-plate tectonics, and people try to describe it with smaller and smaller plates and subplates. Okay, They give it more names like the Capricorn plate and this and the other, but it doesn't, it doesn't exactly fit the perfect model of plate tectonics. So plate tectonics has been a very useful model at probably about the 90% level, okay? But otherwise, there's still a lot of refinement. And in addition to that, we don't entirely understand why it occurs at all, which is, of course, one of the things that I work on, okay, and others in our field, is why it even happens. Because if we look at other planets, like Venus and Mars, that it's harder to see whether there's plate tectonics. We think of them as more normal, and Earth is sort of an anomaly. And so there's still a lot of work to even understand why we have plate tectonics, and even some of the other levels of what type of deformation occurs, in places like the Indian Ocean.
So we actually have a question about could plate tectonics have operated on Mars?
Well, there is evidence, some evidence that, I think Anian would probably better be to answer that, but there was some evidence for one of the major pieces of evidence for plate tectonics on this planet were these magnetic lineations, which I wish I had time to talk about. But there was some evidence for magnetic lineations in some small portion of the southern hemisphere of Mars. Hard to resolve because there are satellite observations. So there's certainly enough crustal activity and motion, so it's thought that perhaps at best there may have been plate tectonic motion early on in Mars's history, and perhaps it stopped. It was because it's small and lost enough of its heat and energy to basically become less active or less powerful enough to drive plate tectonics. That's speculation. One day we'll discover that there's maybe plate tectonics on Mars and Venus, and we say there is not because we don't have enough information. So a lot of it is from ignorance. But
next question. What is the relationship between the plate locations near the oceans and the land masses? Did one form another?
Well, anybody else want to? It's hardly a coincidence. We sort of think in the simple-minded view the continental crust tends to be swept towards where the plates are coming together, sort of like being swept towards the drain of a bathtub, right? So where there are subduction zones, this is where the plates are heavy and they're sinking sinking into the mantle, and the crust on top basically follows behind it. Also, where continental crust is formed, usually is associated with where these subduction zones form. Where subduction zones form, they create melting, the sort of volcanoes, these explosive volcanoes that I mentioned. This is also where most granite on the planet is formed. And most continental crust is really made of granitic rock, okay? So it's not a surprise that continents form in and around subduction zones. They're drawn towards subduction zones. They're sort of built up by the convergence over them. So the fact that plate boundaries come up against continental margins is not, it's not a coincidence, okay? And it's also, okay, we keep going on, but that's good enough for there. Okay?
All right. If India is part of a bigger plate, how did it move across the ocean by itself?
Want me to answer?
Go ahead.
Well, so it actually didn't move by itself. It separated from Gondwana and sort of Africa, Antarctica, and so on. But it had a whole ocean ahead of it. Ahead of the subcontinent of India, there was a huge ocean, right? A huge oceanic plate, just like North America has part of an oceanic plate, just like the Pacific. But India had this one, sort of to the north of it today. And all of that has gone down in the subduction zone until the continent came up against Eurasia once the entire ocean was subducted and it formed the Himalayas. And that's what's probably going to happen once the Pacific is consumed, right? We will, North America will hit some part of Eurasia and form some big continent.
Yeah.
It will happen, right? We won't be alive, but it will happen.
All right. Going back to the question of life on Earth, could changes in the rate of magma convection affect the climate?
Well, it's a complicated system in terms of the climate. As I explained very quickly at the end, is sort of in the long geologic term determined by the rate of mineral exposure and how quickly those minerals wind up reacting with CO2 in the atmosphere. So it's not just a matter if I spew more magma onto the surface, am I going to draw CO2 down faster? It also depends upon the rate at which rainfall is falling on these rocks and whatnot. But you certainly need to have that ongoing mineral exposure to continue to draw down CO2 very, very slowly. So I think to say that if I were to, to spew more magma onto the surface, it would draw down CO2 faster, probably not. We've drawn down most of it already. When people worry about 450 parts per million in the atmosphere now, from our activities, it's still a small number. It's still it's a trace amount. It's just something that we won't put up with very well because we're not used to being in an environment that's much warmer than, a few degrees warmer than we're at now. So chances are probably not.
All right. So I have a card here with probably about 20 questions. I recommend you come and talk to the speaker after the talk. But I will pick one of the questions. What is the biggest volcano in the world?
Wow, the biggest volcano.
Well, the tallest one is Aconcagua, right? In the Andes, I think. Is that true? Is that correct? Yeah. I don't know if it's the biggest, but it's certainly the tallest.
Yeah, Mauna Loa is the biggest shield, right? So Mauna Loa is, one of the biggest mountains on the planet in terms of.
Well, if you count from the bottom of
Well,
the
yeah,
ocean.
but if you count on the bottom of the ocean, but sure, but it's built up from there, but yeah.
And Olympus Mons on Mars is
Much
much bigger
than
all of these.
Right. Depends on what the population is around it. Right? Fuji?
Montpellier, yeah, that's a good one.
Yeah. Oh, Dave, what do you think? Oh, throw the question back at you.
Great question, great answer. How hot is the magma?
Well, okay, it depends. What the temperature of the magma coming out of Hawaii is, what is it, like 11, 1300 something? Yeah, degrees centigrade. This is in centigrade. Yeah.
And why is the crust so thin? I thought it was thick.
Well, okay. I'm saying it's thin relative to the rest of the mantle. So, oceanic crust at the bottom of the ocean is 7 kilometers thick. Okay, and we compare it to the thickness of the mantle, which is, almost 3,000 kilometers. Okay, and thickness of the continental crust is on average 40 kilometers. So that's thicker. We can't drill to the bottom of the continental crust. We can't really even drill. Well, we've gotten 20 kilometers in drill holes, but not much deeper than that. So it's thick-ish, okay, if you're a crustal geologist. But if you're a mantle person, it's the sludge. Sorry.
All right, another card with lots of questions. One is about spreading centers that indicate crustal expansion.
Obviously, these people were not listening to my talk.
Now, this is a good one. I find it hard to believe crustal spreading volume is exactly equal to subduction volume.
Well, otherwise, yeah. Does somebody else want to do that?
Otherwise, the surface of the Earth will be expanding or shrinking.
Right. If you were eating up the crust faster than you were creating it, then you would just shrink out the crust. If you're doing the other way, you would expand it. So you've got to balance the two of them. So you have to destroy the plates at the same rate that you're creating it. So.
But we actually have, there are measurements, right? Jean-Luc can perhaps talk about geodesy. We can figure out that the Earth's radius isn't getting bigger from certain measurements of the orbit of the Earth and things like that. So we know from observations now that the radius isn't getting bigger because that would have consequences.
Right.
All right, and I love this last question. How about changing up the moderator at your events? I love it. This is an invitation to all of my colleagues to please volunteer to do this.
Oh, yeah.
I have to wait for the next chair.
We'll close here. If you have additional questions, please come and talk to our panelists. And I want to thank our speaker again.
Thank you.
And I forgot your gift.
Oh, I have
We have a gift for you.
Do I have to open open it in front of everybody? No. All right, here goes. Oh, wow, this is fantastic. It says UCLA, the first century.
All right.
Wow, thank you very much. Okay.